Here, I want to show you how to use numerical method to solve this viral question. First, what is Newton-Raphson method? I'm going to introduce it to you shortly. But the first thing we need to do to use Newton method is that we need to find a function. And the function f of t, this is the way we find that. So when you look at the equation, what we need to solve for, we have t raised to power t equals 49. So to get a function, actually, you can isolate everything that you have to one side of the equation such that the rest, all of them will be equal to 0. Because what we need actually is that we're trying to find a solution to that function. So if we make that whole thing equals 0, then we can label it the function. So here, I've been able to take 49 to the left hand side, which is negative 49 now, and then t raised to power t minus 49 equals 0. So we have f of t equals t to the t minus 49. Now the next thing we need to do is that we need to find an interval that contains the solution. Typically, what we're trying to do is that since the interval is unknown in this place, we can make a calculated approximation of what the interval that contains the solution will look like. And how can I do that in this place? So you would realize that if you go back to this particular equation that we have up here, now in this equation, you would notice that if you put 3 to the power of 3, that's 27, and that is not up to 49. But the moment you move to 4 and you put 4 to the fourth, that is 256, which is greater than 49. That implies that we have skipped the solution in between 3 and 4. So 3 and 4 is a great interval to put. So between 3 and 4 is a great interval to put as what contains the solution. However, you can decide to use 2 to 5. You can decide to use 1 to 7. You will still get your result, just that it might take you a longer time. And one way to test if an interval contains the solution to a given problem is that find the value of f of the left endpoint and find the value of f of the right endpoint. Now, when you find the value of these two guys, if you find the product, they will be less than 0. So what I mean by that is that if you put f of 3 in this place, you get your result, and you put f of 4 and you multiply the two of them, it's going to give you a result that is less than 0. That is how you test if an interval contains your solution. Just pick the endpoint, evaluate the function at those points, and find their product. It must be less than 0. And this is the formula itself, the Newton-Raphson iteration formula. What this is telling us is that the next value of t, that is tn plus 1, is the previous value minus f of tn, then the derivative of f at that tn as well. So basically this is saying that if you want to find t1 will simply be t naught minus f of t naught minus f prime of t naught. So, and this is an iteration, meaning that when you get one solution, use this present solution to get the other solution. So quickly, I completed my derivative of f of t in this place. In case you don't know how to find the derivative of functions like this, 2 to the t to the t, you can write it using the exponential form, such that you have e to the power of ln of t raised to power t. With that, it's going to be easier for you to solve. So let's proceed. We have the initial guess. Now, this initial guess, normally when you are doing numerical methods, you probably might be given what your initial guess should be like. Now, but sometimes you'll be the one to make the guess. And since you already know what your interval is, so just pick a random number in that interval, any random number of your choice. I could have picked 3.9, I could have picked 3.4, I could have picked anything as long as it is in this interval. So you can try that as well. Pick any random number. So I picked 3.3 here. So what does that mean? That implies that my t naught equals 3.3. Then if I use that in this expression, that implies that t1 equals 3.3 minus f of 3.3 divided by f prime of 3.3. So what's left for me to do is to just substitute everything I have here into the equation. Just substitute that into the equation. So when you look at that, so you put all of this in your calculator and then you get this result. Now, one thing is that if you're using a scientific calculator, you can actually do this thing a lot faster than um, pressing the whole thing one after the other. So what you need to do, so if you see from my calculator here, is that press 3.3 and press equal to sign. So with that, it will provide 3.3 as an answer. Then when you are done with that, what you want to do is that you want to press the AC button. Don't use the power on button. Now when you press that, it has programmed that 3.3 as an answer. Now, so when you want to type in your stuff, you'd realize that instead of typing 3.3, so as you can see on my screen here, instead of typing 3.3, what I'm typing is answer. So I will just put, for everywhere there is 3.3, I will just put answer. So I can see answer minus, then parentheses, answer raised to power answer minus 49 divided by answer to the power of answer, then open a parenthesis, 1 plus ln answer. Now, that gave me 3.2786. That is my T1. If I want to get T2 as well, all I have to do is to plug in this value that I got for T1, plug it in into the expression again. But now that I've already programmed that in my calculator, make sure that in your calculator you are always pressing answer. And sorry, you're always pressing AC instead of the power on button. So with that, I've been able to program the previous answer. So programming the previous answer now, I can just press the arrow left or right button, whichever one I decide to press. Then once I press that, I can press equal to sign again. The answer that is there now is going to be the new answer that I've gotten. And with that, I can continue to repeat this thing and get the result. But if you were writing, let's say, a theory exam, you would have to like rewrite all these formats. But instead of computing all these things, you just know what the final answer is going to be like on your calculator. So you saw that as I pressed it. And then how do you now know where to stop in this Newton's method? If you look at it, T2 and T3, they are approximately the same thing. When you begin to have answers that are closely alike, like this, then that's your best approximation. So that implies that the value of T is actually 3.27803. And that's it. That's how you apply numerical method. So when you see similar problem like this as well that give all this kind of headache online, numerical method is just the surest way to go about it, and you'll be fine. I guess I'll see you in the next one.